Okay, nice. Hello, guys. So, today we're going to be going over another topic of number theory called modular arithmetic. So, this is a pretty hard concept to learn, but once you understand it, it is pretty easy. And it can help you solve a lot of problems like pretty quickly. So, basically, the reason why we're learning this right now is because we sort of already learned how to do some of this before, right? So, for example, last class we were working on units digit of 468 to the power of 357, right? So in this case, we know that we only care about the units digit, right? So it's the same thing as 8 to the power of 356. And we know that the exponents of 8 repeat every like 4, right? So they repeat like 8. 8 times 8 is 64, ends in a 4, times 8 again is 32, ends in a 2. Times 8 again is 16, ends in a 6, right? So if we try to multiply this by 8 again, we'll just get 8, right? So it repeats every 4. So in this case, if we want the units digit of this number, all that we have to do is oh, 357, my bad. All we have to do is calculate like which one of these is in which one when divided by 4, right? Because we say, oh, 356 is a multiple of 4, right? We know this is a multiple of 4. And that means that 8 to the power 356, because this is 1, 2, 3, 4, all multiples of 4 are going to have 6, right, as their remainder. Well, as a unit digit, right? So since this is a multiple of 4, it's going to have 6. So this is going to have a unit digit of 6. Well, since this, when you divide this by 4, it actually has a remainder of 1, right? So this is going to be 1 more than that, and it's going to go to 8. So this one is going to have a unit digit of 8. So this should all seem pretty familiar to you because we went over these types of problems last class. But this is actually an example where we sort of like tried to use a little bit of modular arithmetic. So in the next example, we have the decimal expansion of 2/7, and we're asked the 100th digit to the right of the decimal, right? Not the 100th digit, right? But the 100th. So, and two, in the sevens, can anyone tell me like what the rule was for like decimal places, decimal points or sevens?
They're like the digits 142857, but they start in different places.
Yeah, so 142857, right? So 0 point this repeating. And basically, we actually this is 1/7, right? So this is 1/7. So in 2/7, I can give you guys like a little formula here. It's like 2A5714, I'm pretty sure. Or it's something like this. Anyways, what we can do is we can just say, oh, we want the hundredth digit, right? And we know this repeats every 6. So when we divide 100 by 6, we get a remainder. We get like, so we know that 96 is a multiple of 6, right? So we get a remainder of 4. Remainder of 4, right? So in this case, since the remainder of 4, we just count, oh, 6s and then 1, 2, 3, 4. So our answer is going to be 7. It's going to be, the j is going to be a 7. So as in this case, we just found the remainder of 100 over 6, and then we just took that as our answer instead. And then our next example has to do with clocks. So we're going to assume that this is like a 12-hour clock, like the round ones. And then and it's currently 5 o'clock. So what time will it be 1,000 hours from now? So we know that every 12 hours, we can just cancel it out, right? Because if we go with 12 more hours, then that's just going to bring us back to whatever time it was before. So we can just cancel out all the multiples of 12 from here, right? So if we just do 1,000 divided by 12 on 8, this gives us 96, 40. 83, 3 times 12, 76. Okay, so this has a remainder of 4, right? So basically, instead of asking us this many hours from now, right, it's asking us, we first go through 83 12 rotations, and those don't change anything, so we don't have to worry about them. So basically what it's asking us is what time will it be 4 hours from now? And in this case, it will be 4 hours after 5 o'clock is 9 o'clock. Yeah, the answer is going to be 9 o'clock. So, in this case, what we've basically been doing is modular arithmetic, right? So modular arithmetic is basically a, like a smart way of saying we want to look at the remainders, right? So in this case, we would have something mod something, right? So for example, in this case, we would have like 1 mod 12. We can pronounce that as 1 mod 12. And basically, a modulus is the length of the repeating block, right? So as in before, like if we wanted to find the remainder of something when divided by something, right? So we have a number A, we want to divide this by X, right? So this is going to be our modulus. And then the remainder is going to be like the number that we have, right? So two numbers are considered congruent if they leave the same remainder when divided by the modulus. So for example, we have 13 is congruent to 1 modulo 12 because both 13 and 1 leave the same remainder when they're divided by 12, right? So if you want to write them in a shorthand way without writing out the whole sentence, 13 is congruent to 1 modulo 12, you could just say 13 is, this is a congruent sign to 1 mod 12. And you have to write like the 1 mod 12, right? So mod 12. And basically, notice that the congruent symbol has 3 lines, and we'll talk about this a little bit later. So for modulus 12, generally, if it's looking for one answer, it's looking for a number between 0 and 12, right? 0 and 11, right? Because 12 is congruent to 0 mod 12, right? Because 12 minus 12 is just at least the remainder of 0 when you divide out by 12, right? So this three line equal symbol thing is called is congruent to, right? It doesn't mean is equal to, because our numbers like negative 12, 0, 12, 24, 36 and stuff, like when you take the mod 12, they're all the same, they're all like congruent, right? But they are not equal. Obviously, like these numbers are not equal to each other, right? But when you take the mod 12, they are congruent to each other. So that's why we use this separate symbol to denote this. And two numbers, A and B, are congruent if modulo M is a difference. A minus B is divisible by M. So this is like a little bit confusing, but basically what it's saying is that A is congruent to B modulo M, so mod M, if A minus B is congruent to 0 mod M, right? Because we know that if it's divisible by M, that means that it's like, if it's divisible by M, that means that it's congruent to 0 mod M, right? Because it leaves a remainder of 0 when you divide it by M. So basically, these are basically the same thing. Okay, so to start off with, let's do a couple of easier examples. So in this example, we have what are the 5 smallest positive integers greater than 5, which are congruent to 3 mod 5. So in this case, we have 3 mod 5, right? And we want to find numbers mod 5. And we want to find numbers x that's congruent to 3 mod 5. Right? Because that's basically what they're saying in the problem. So we have the 5 smallest positive integers. Well, obviously, -2 is congruent to 3 mod 5, right? Like, even though like dividing a negative number, leaving it bigger is kind of interesting, but we know that if we add 5 to -2, it's basically adding 0 to both sides. We can just say, oh, that's just going to be 3, right? -2 can go to 3 mod 5, but it says positive integers, so we can't do -2. So instead we're going to add 5, right? So we have x is congruent to 3 mod 5. So if we add 5 to this, it's going to be 8 mod 5, right? So it's going to be 8 is congruent to 3 mod 5, because we have 8 is going to 3 plus 5, right? And then we know, what is 5 mod 5? Can anyone tell me? In other words, what's the remainder when you divide 5 by 5?
3.
When you divide, okay, let's do this real quick. So when we divide 5 by 5, it divides evenly, right? So we have a remainder of 0. So 5 is actually 0 mod 5. So we can just replace this 5 with a 0 because it's 0 mod 5. And we're saying the same thing. So it's going to be 3 mod 5. So A is congruent to 3 mod 5, right? So we have 8 is a possible solution. And doing it like this, we can just add 5 each time, right? And still have the same number. So we have 8, and then 8 plus 5 is going to give us 13, plus 5 is going to give us 18, plus 5 gives us 23, plus 5 gives us 28. So these are going to be the 5 smallest positive integers. Okay. If you have any questions, you can ask me. Okay, so in our next example, we've actually done this problem before, like a couple minutes ago, but the question where it's currently 5 o'clock, what time will it be 1,000 hours from now? But this time we can solve using modular arithmetic, which is a bit easier. So, well, a bit easier to understand. It's sort of about the same length since the problem is pretty easy. But basically what we said is we want to like say, instead of dividing this by 12 and like sort of logicking it out, all we need to do is take 1,000 mod 12, right? Because we can say, oh, we want 1,000 mod 12 because this is going to be the number of integers that are, this is going to be the number of integers that have like, no, this is going to be the integer that's is left when we divide 1,000 by 12, right? So the reason why I want to do this is because 5 o'clock, like if we add 12 hours to 5 o'clock as before, we just get 5 o'clock again. So we want to cancel all those out by taking this mod 12. And in this case, we still sort of need to do the thing of like just dividing this out. And we found out the remainder was 4 last time. So this is congruent to 4 mod 12, so 4. And basically what we're going to do is we're going to say, we just have 4 mod 12, so we just add 4 to this and 9 o'clock as before. So as you can see, like modular arithmetic sort of provides like an easy to understand solution for this. So next, we're gonna have like a check for understanding. So I'm gonna have you guys do these questions really quick and send me your answers in the chat when you're done. I'll give you guys like a couple more minutes to do these questions. I can also explain. Nice. So, Kevin, you have the first question is correct. The third question is correct. The second question is correct. Okay, good job. Okay, so I'm gonna start explaining now. So we have that basically taking something modulo 12 is asking us about the remainder when it is mod 12, right? So we have 1000. What if the 96 is 12 times 8, right? So basically what we're gonna do is gonna say, oh, it's 4 more than a multiple of 12. So we're gonna use the remainder 4. So 100 is congruent to 4 mod 12. So that's just 4. So next, with these two bigger numbers, it would be sort of hard, right? And it sort of defeat the purpose of modular arithmetic if we were just going to say, oh, we're just going to divide each of these by 12, because then modular arithmetic would be kind of useless, right? So actually here we have, for this question, we have two different ways of doing it. The first way is sort of like generalizable. So we just take both sides of this equation and we can multiply them by 11, because we know if we multiply both sides by the same thing, we can get good things happen, right? So we have 11 times 100 is congruent to 4 times 11 mod 12. And then we have 1100 is congruent to, you could say 44, or you can notice that 11 is going to be -1 mod 12. But we're just going to be 44 here to keep it simple. And then we know that 44 is not like a legitimate number, right, in mod 12, because we can't say, oh, I divided this number by 12 and we had a remainder of 44 when we divided it out, right? So in this case, we would just take this. 44 is actually congruent to 44 minus 36 mod 12, right? Because 36 is technically 0 mod 12, so it's going to be 8 mod 12. And then the second way you can sort of do this, as you can notice that this is 1100 is going to be 1200 minus 100, right? And we know that 1200 is actually going to be 0 mod 12. So it's going to be 0 minus 4 mod 12. So that's another way you can do it. So -4 is just 8. Did I? Oh, over here. All right. I forgot the congruency symbol. Anyways, for this 3300, we can also do it in sort of the same way, right? So we know that 1100 is congruent to 8 mod 12, right? So all we need to do is multiply both sides by 3. Right, so we have 3300 is congruent to 24 mod 12. So 24 mod 12 is congruent to 0 mod 12, because 24 is a multiple of 12. So as you can see, instead of going through like and dividing each of them by 12, modular arithmetic makes it really, really easy to just multiply everything together to get like bigger and bigger numbers. So in this case, we exhibited one of the two general formulas that we'll be using for modular arithmetic. So the first is, if we have a number A is congruent to X mod n, and then B is congruent to Y mod n. And also, like, sometimes people put parentheses around like the mod n. It varies based on what book, like what source you're looking at, but yeah, just keep in mind sometimes you do that. And then we have A plus B equals X, that's congruent to X plus Y mod n. So all we need to do is just add the same thing on both sides, right? Because you know that B is the same thing as Y in mod n, right? So all we need to do is add A plus B congruent to X plus Y mod n. Because these mods have to be the same in order for you to do this, right? If one is like 3 and one is 5, obviously it's not going to work. So it's sort of like the same thing as equality. Just in this case, it can be more general because, for example, in mod 12, you could add like 3 to one side and 12 to the other side. No, 3 to one side and 15 to the other side, because they're technically the same thing, mod 12. So that's just something to keep in mind. And the same thing for multiplication, you can just do AB as congruent to XY. Yeah. So mod n. As before, B and Y can be different numbers. You don't have to be the same thing. So for example, you can have like 3 times A equals 15 times X or something. Okay. Yeah. So with the next example, we have this guy named Parker, and every 12 hours, his clock is a little fast, right? So his clock advances 19 hours. So if Parker's clock is correct at 6 a.m. on the morning of June 1st, what time will his clock read at 6 a.m. on the morning of July 1st? So we know that, first of all, we need to know how many days June has, right? So it's not that hard. You can just like have those memorized. So June actually has 30 days, right? So it has 30 days, and each day is 24 hours, right? So this is going to add up to 60 like 12-hour chunks. And in these 60 12-hour chunks, Parker's clock is going to go forward 60 times 19, right? And so this is Parker's clock. This is how many hours it has, right? So right now his clock is at 6. After going through this many hours, what time will his clock read, right? So actually all we do is the same thing as the other clock problem. We take this mod 12, right? And we know instantly that 60 is 0 mod 12, right? So just 0 times 19 mod 12. And we know that this is going to be 0, right? So we have 0 times 19 is going to go into 0 mod 12. So we have that our time actually doesn't change. So it's going to be correct. His clock is correct on 6 o'clock in the morning. So it'll read actually 6 o'clock. So it'll read 6 o'clock. Okay, nice. So basically, before all we've done is doing problems that sort of like, they're pretty easy comparatively, right? But it's just like, oh, well, modular arithmetic, like maybe it's like a neat little trick to use, but like it doesn't really make anything that much faster. Well, in this question, it actually does, because as you get to more complex problems, modular arithmetic is actually like a really, really quick shortcut to a lot of questions. So for example, we're asked, what is a remainder when this big thing is divided by 8? So at the beginning, this sort of looks pretty scary, but if we separate the terms and calculate them each individually, it actually makes it a little easier. So let's just do that. So 3 to the power of 1 obviously can go to 3 mod 8. 3 to the power of 3 is 27. Right? 27 is obviously can go to 3 mod 8 because 24 is 0 mod 8. Right. And then 3 to the power of 5. Well, this is just 9 times 27. And this is just 9 times this, right? Right? Because it's like 3 to the power of 2 times 3 to the power of 3. And we know that this is 3 mod 8. So you just can substitute this in for 3 mod 8. And we know that 9 times 3 is 3. So the answer for this one is going to be 3 mod 8. And we notice that, oh, all of these look like they're going to be 3 mod 8. But let's see why they're all 3 mod 8. So as you go from one term to the next, right? 3 to the power of 1, 3 to the power of 3, right? Since they're all odd, this number is 9 times this number. So can anyone tell me what 9 is in mod 8?
1.
Yeah, good. So 9 is 8 mod, no, 9 is 1 mod 8, right? So now that we know that 9 is 1 mod 8, basically what we're doing is we're multiplying 3 by 1 every single time, right? So the first thing is 3, and we're multiplying 9, so we're really multiplying by 1. So 3, multiply by 1, get 3, multiply by 1, get 3, right? So we just keep on multiplying by 1, and we just end up with a bunch of 3's at the end. So we know that this sequence over here has 15 terms. And each of these terms provides us with a 3, right? So, and yeah, we're gonna have 15 times 3 term, 15 times 3, which gives us 45. And notice that 40 is 0 mod 8. So 45 is congruent to 5 mod 8. So our remainder is going to be 5 when we take this mod 8. So generally, like this is like a really easy way of solving the problem, right? Well, of course, you could have looked at the pattern before you without modular arithmetic and found, oh, we can just see that they're all going to be 3. But this just modular arithmetic helps us understand why all of the terms are going to be 3. So next, we're going to prove the divisibility rule for 11. Remember a long time ago when we were doing divisibility? Back at the beginning of number theory. Well, today we are going to prove one of the divisibility rules. And this one is actually quite complicated. So let's just take an easy case at the beginning. A, B, C, D. Our number is going to be A, B, C, D. Not like A, B, C, D multiplied together, but like A in the thousandths place, B in the hundredths place, C in the tens place, and D in the units place. So here we have this is just going to equal a times 10 to the third power plus b times 10 to the second power plus c times 10 to the first power times d. Oh, no, plus d, plus d. Right? So in this case, we want divisibility, right? So whenever we talk about number theory and divisibility, we should automatically think of using modular arithmetic because that's just finding remainders, right? So either remainder is 0 or the remainder is not 0. If the remainder is 0, then it's divisible by 11. So in this case, we have this. We want to take this mod 11, right? So mod 11. So it's going to take about 11. Just going to just make it make sense. And at first this seems like a little bit untransmogrifiable, right? So anyways, we obviously can't do D mod 11. We can't simplify D mod 11 because we don't know what D is. But let's look at the 10s. So what is 10 mod 11?
-1.
Yeah, so 10 mod 11 is going to be -1 mod 11. And in case you didn't know, this is because we just do 10 mod 11. So this is congruent to 10 minus 11 mod 11, right? And then this is just -1 mod 11. So here we just have 10 is -1 mod 11. So we just minus 11. So in this case, instead of having this, we just have a times -1 to the third power plus b times -1 to the second power plus c times -1 plus d, right? And then actually what we're going to do here is we're just going to multiply this out. So we just have -a plus b minus c plus d. And as you can see, this is actually the divisibility rule for 11. We just take the alternating sum of the digits, right? So actually, if this is congruent to 0 mod 11, then we have that a whole number, A, B, C, D is congruent to 0 mod 11, right? And you can actually generalize this, and we can say, oh, if we have a to the power of n, a to the power n minus 1, a n minus 2, that's not a to the power of 1. So, no, not a to the power of 1, a of 1. So if this is a number, right, we can just have, this is congruent to a n -1 to the n minus 1, I think. So, and then plus da da da, right? I'm not gonna write all the terms here because obviously that'd be impossible, but we're just gonna take out a to the n times -1 to the n minus 1. And note that like if we take -1 here, if we have a negative here, we have a positive next, and then a negative, right? Because we're multiplying by -1 every single time. So it's just gonna be the alternating sum again. Okay, no. So there we have it, the divisibility rule for 11. So here are some practice for y'all. I'll give you guys like a couple minutes to do these. The last question is kind of hard, but I'm confident that you guys can do it. So I'll give you guys a couple minutes and send me answers in the chat when you're done. Yes. So Kevin, the answer number 1 and number 2 are correct. I would double check the answer for number 3 though. Okay, so I'm gonna start explaining now, and if you guys figure out any of the questions while I'm explaining, feel free to send me. So anyways, for question 1, we have this person named Priyanka, and basically she writes her name over and over again on a sheet of paper, and then she completes 995 letters, right, before the paper is taken away. So what is the last letter she writes? So basically, first we see how many letters she has in the name. 1, 2, 3, 4, 6, 7, 8. So 8 letters total, right? And then we want how many 8-letter things are in 955. So you're saying 955 mod 8. And then so because every single 8 letters just starts over and over and over again, right? So we take this mod 8. So we have 955 is congruent to, let's read it. 955 is congruent to 155 because we just minus 800. It's congruent to -5 because 160 is 0.5, right? So it's congruent to 160 minus 155, which is -5 mod 8, which is congruent to 3 mod 8. So this is 3 mod 8. And then we're not done yet. The answer is not 3 because we asked what's the last letter she writes. So we have 3 letters, right? So 1, 2, 3. So the third letter is going to be I. So the correct answer is I. So next we have, what is the remainder when this thing is divided by 50? So first, whenever you see like a sum like this, that's obviously has a formula, you should probably write it in the formula. So 48 times 49 over 2, which equals 24 times 49, right? So next we notice that we want to take this mod 50. Right, mod 50. And then we notice that 49 is actually going to be -1 mod 50. So instead of doing this, we can just say this is congruent to -24 to the power of 49 mod 50. Right. So actually, instead of doing this, we can write this in the parentheses and make this 26. So instead of doing this, we're going to do 26 mod. So actually 26 to the power of 49, nobody has any like straight up things to do then. So we're just gonna take this and like dash it out. So 26 to the power of 1 obviously is gonna leave us 26. How about 26 squared? 26 squared gives us 676. Right, it gives us 676. I hope I remember this correctly. So mod 50, this is going to obviously be congruent to 26 mod 50, right? Which means that no matter what exponent it is, we have 26 multiplied by 26, we get 26 again. If we multiply this by 26 again, we just end up with 26. So it doesn't matter what the exponent is, it's going to give us 26. So our answer is going to be 26. And then, let me erase all of this. We have for our third problem, what is the smallest positive integer multiple of 31 that leaves a remainder of 1 when divided by 13? So basically, when divided by 13 gives us mod 13. So we have something mod 13. And then we have, so let's say it's a multiple of 31. So let's say our number is going to be 31x, right? So this is congruent to 1 mod 13, right? So In this case, this is actually kind of hard, but we realize that 31x, we can actually just say that this is 26x plus 5x. And 26x is obviously going to be a multiple of 13. So we can just get rid of this and we just say 5x, this can go into 1 mod 13. So in this case, we want to make this side a multiple of 5. So we have 5x into 1 mod 13. Which is congruent to 14 mod 13, which is congruent to plus 13 again. We have 27 mod 13. Plus 13 again, we have 40 mod 13. So actually we can stop here because we know 40 is actually a multiple of 5. Because notice that as like in regular things, you cannot divide by something in modular arithmetic, right? Because dividing is simply not an operation when you're doing modular arithmetic. You can't just say, oh, 5x equals 1 mod 13. So x is equal to 1/5 mod 13, right? It just doesn't work that way. So in this case, we have x equals 8 because 5 times 8 is 40. So x equals 8. So we have 13x equals 31x. X equals 13 times 8, which equals which equals 31 times 8, which equals 248. So this is 248. And notice that if you guys want to learn more about this kind of stuff, equals 1, and like how to do division in modular arithmetic, they're called inverses. And basically what they're saying is, as you multiply something by this number, it's going to equal 1, right? So it's like a sort of shorthand way of dividing. Because if we say 5x equals 1, congruent to 1 mod 13. So the modular inverse of 5 mod 13 is going to be 8. So which means that if we multiply both sides by 8, this just gives us x equals 8. Congruent to 8 mod 13. So such a modular inverses if you guys want to learn more about that. Inverses. Okay. So anyways, if nobody has any questions, that's going to be it for today. Okay, guys? No questions?
Okay.
Okay. Then I'll see you guys next time, okay? Bye.
Thank you. Bye.
And